Accelerating grasp exploration by leveraging learned priors. Robotic grasping has a wide range of industry applications, such as manufacturing, warehouse order fulfillment, and assistive robotics. Grasping is a difficult problem due to uncertainty in sensing and control. General-purpose grasping algorithms can fail to generalize to certain objects, such as objects significantly out of the training distribution, or adversarial objects for which very few high-quality grasps exist. This motivates for a method that learns to grasp an object of unknown geometry by repeatedly attempting different grasps. First, we discuss prior work on both analytical and data-driven methods for grasping. Analytical grasping methods assume knowledge of the geometry of the object to be grasped, or use geometric similarities between known and unknown objects to infer grasps on unknown objects. However, the generalization of these methods is limited for objects dissimilar to the known objects, or when geometric information is unknown, as in the case we consider. Data-driven grasping policies have achieved success in learning general strategies for grasping arbitrary objects. These methods train a deep neural network on the labeled data to predict grasp quality, or directly plan reliable grasp on novel objects. Data-driven grasping methods rely on labels from human, self-supervision across many physical trials, or sim-to-real transfer methods such as domain randomization or domain adaptation. The presented method aims to leverage learned grasp quality estimates to enable efficient online learning for difficult-to-grasp objects through physical exploration of one pose of one object at a time without previous knowledge of the object's geometry. Here, we discuss the problem statement. The observation is an overhead depth image of the object before policy learning has begun. The image captures a single stable pose of the object. Secondly, we define a set of K-arms, each with a corresponding grasp action UK. The rewards for each arm are drawn from a Bernoulli distribution with unknown parameter pk. Here, reward of action UK is equal to 1 if executing action UK results in the object being successfully grasped. Otherwise, the reward is 0. Fourth, we assume access to priors on the Bernoulli parameter pk for each arm k. The prior distribution of pk is denoted as the prior. Fifth, let pi theta of uk denote a policy parameterized by theta, which selects an arm k and executes the corresponding action uk. Therefore, pi theta of uk defines a distribution over the action space at any given time step t. Last but not least, the objective in policy learning is to maximize the total accumulated reward, which corresponds to maximizing the frequency with which the object is grasped successfully. Let ET denote the action selected at time t. Then, the objective is to learn policy parameters, theta, to maximize the total reward accumulated over time. Here, we discuss the assumptions. First, we assume that the object remains in the same pose during all rounds of learning. Secondly, we assume that the robot can evaluate whether a grasp has succeeded. We use a pre-trained grasp quality convolutional neural network from DexNet 4.0 GQCNN to obtain an initial estimate of the probability of grasp success. GQCNN, there's a Q function, Q phi, which, given an overhead depth image and the proposed parallel jaw grasp, estimates the probability of grasp success. However, as explored in works on adversarial objects, there exist many objects for which the analytical methods used for training GQCNN are inaccurate, resulting in significant errors. Thus, we refined the initial GQCNN grasp quality estimates with online exploration. To measure the quality of the GQCNN prior, we define a notion of the similarity between the prior and the ground truth grasp probabilities, termed the prior mismatch. We present a new metric based on the discrepancy between how arms are ranked under the prior and under the ground truth distribution. The Kendall's-Tau coefficient is a value between -1 and 1, where 1 denotes a perfect match in the ranking, and -1 denotes a perfectly inverse ranking. We define the prior mismatch M as a dissimilarity measure that maps tau to a range between 0 and 1. We did not choose L2 distance because the exact Q values and exact ground truth values do not matter as much as the ranking in terms of determining which arm the Thompson sampling algorithm will pick. The method consists of 2 steps. First, we compute priors from GQCNN. Secondly, we update priors through Thompson sampling with a beta Bernoulli process. Here, we discuss the problem overview. Given the initial observation O, arms are sampled under observation. Then, a pre-trained GQCNN is used to set the priors on the reward parameters for each arm. At each time step, the learn policy selects an arm and executes the corresponding action in the environment. Based on the received reward, the Thompson sampling parameters, alpha and beta, are updated. To leverage neural network priors, we compute Q phi for each arm, and we use these estimates as each arm's initial mean Bernoulli parameter. Note that the prior strings S, which is the sum of alpha K0 and beta K0, can be interpreted as the number of pseudo rounds before policy learning. If S is large, the prior induced by S will significantly influence the expected Bernoulli parameter PK for many rounds. If S is small, the resulting prior will be quickly washed out by samples from online exploration. We want the expectation of PKT to be the Q value of the corresponding grasp EK. To achieve this, we set alpha and beta accordingly. Here, we discuss the Thompson sampling algorithm in more detail. At time t, the policy samples PKT from the beta distribution parameterized by alpha KT and beta KT for all arms. The policy then selects arm K star corresponding to the high sampled PKT. It executes the corresponding action in the environment and receives a binary reward indicating the success of the grasp. It performs updates of alpha and beta values. We conduct simulation experiments across object poses with a wide range of prior mismatches M, as shown in Figure A, which plots the frequency of prior mismatch values over around 4,000 object poses in the dataset. In Figure A, the x-axis are the prior mismatch values, and the y-axis are the number of object poses that has the prior mismatch value. When the prior mismatch is low, we expect policies which give more weight to the prior to perform well. If the prior mismatch is high, we expect policies which prioritize online exploration to attain higher rewards. Figure B shows policy performance as a function of prior mismatch. The x-axis are the prior mismatch value bins. The y-axis is the cumulative reward for each policy. The pink bar is the ground truth policy. The brown bar is the greedy policy. The blue bar is Thompson sampling with a uniform prior. The orange, green, red, and purple are Thompson sampling with learned priors in increasing order of prior strains. When prior mismatch is high, the difference between the different TSLP prior strains is significant. Low prior strains perform better than uniform prior, indicating the GQCN prior is useful. However, too high prior strains also results in low rewards. Note that when the prior mismatch is low, all online learning policies perform well. This table shows the cumulative rewards averaged over 100 trials for each policy. The results show that TSLP significantly outperforms the greedy baseline by 64.5% and achieves within 5.7% to the Oracle baseline. The result here suggests that TSLP is able to successfully leverage priors from GQCNN to outperform GQCNN on a wide range of objects. As a further case study, we select a set of 4 objects, as shown, which are diverse in their shapes and sizes, and vary widely in their prior mismatches M. The first row visualizes grass qualities as measured by GQCNN prior, which is on the left, and the ground truth grass success probabilities, which is on the right. In the second row, we visualize the policy performance for all baselines and TSLP policies. The x-axis is the number of time steps in training. The y-axis is the reward cumulated for each policy. The pink dotted line is the ground truth policy. The brown line is the greedy policy. The blue line is Thompson sampling with a uniform prior. Orange, green, red, and purple are TSLP policies in increasing order of prior strains. As expected, the ground truth policy achieves the best performance since it uses Oracle information. We find that for objects with low prior mismatch, the greedy policy and the Thompson sampling policies, which place high weight on the GQCN prior, perform well. However, for objects with higher prior mismatch, we find that the greedy policies perform much more poorly, and online exploration is critical to finding high-quality grasp. However, even with very high prior mismatch, the gap in performance between Thompson sampling policies that uses prior and Thompson sampling policy with uniform prior indicates that GQCN prior helps accelerate grasp exploration even when it is inaccurate. In future work, we will design new online learning algorithms to explore grasps across the different object-stable poses and extend experiments to new grasping modalities, such as suction. In addition, we'll explore ways to approximately enforce pose consistency in physical experiments. For example, we can use a string to lift the object after each grasp and put it into pose. Additionally, we can detect stable pose changes by evaluating whether the observed depth image changes in a way that cannot be described by planar rotation and translation. In this paper, we present Thompson sampling with learned priors, a banded exploration strategy for robotic grasping, which facilitates use of expressive neural network prior belief distributions and enables efficient online exploration for objects for which the prior is inaccurate. We quantify the notion of prior mismatch as it pertains to the ranking of arms and explores the effect of prior mismatch on efficiency and efficacy of online learning. Experiments suggest that across a dataset of 3,000 object poses, TSLP outperforms both a greedy baseline as well as a Thompson sampling baseline that uses a uniform prior and is able to leverage GQCN prior to significantly accelerate grasp exploration.